So I'm going to have a look at a couple of rather tricky redox titration calculations. Both of these involve permanganate titration, so you should be familiar with the chemistry of that actual titration and the practical aspects of it as well. So in this particular question, we're looking at a polyvalent metal, which is a metal which has variable oxidation states, in other words. And we're going to react that metal with firstly sulfuric acid to oxidize the metal to oxidation state that we have to work out, which is its lowest oxidation state. We're then going to oxidize it further with potassium permanganate to its highest oxidation state, and then we basically have to work out what is the highest oxidation state that that metal has achieved. So let's get going here. I suppose the first thing that you have to remember whenever you're carrying out redox reactions is that one thing is going to lose electrons and the other thing is going to gain electrons. And fundamental to this question is that the number of electrons lost has to be equal to the number of electrons gained. In other words, if you can work out how many electrons one thing is losing, then you can work out how many electrons a certain number of moles of the other thing has to be gaining. And we're going to use that principle to essentially just answer both parts of this question. So let's look first of all at what happens whenever we take this metal. And the first step is that we reacted with dilute sulfuric acid, if you read the question. Now, if you want to have a go at this on your own without me talking you through it, just pause the video and do that. You can come back and check your answer, of course. So we're going to react the metal with sulfuric acid. And when we do that, we end up with metal ions plus sulfate plus hydrogen gas. Now, if we look at that, you can hopefully work out as A-level chemists that the sulfate ions are spectator ions, and that the metal ion has lost electrons and has been oxidized, and that the hydrogen ions in the acid have gained electrons and have been reduced. So essentially, if we can work out the ratio of how many the number of electrons that have been lost, that has to be equal to the number of electrons that are gained. So basically what's happening is the metal is going to the metal positive ion. Now, we don't know what that is yet, plus X number of electrons. The hydrogen ions in the acid will gain 2 electrons to form hydrogen gas. We do know that, okay, from just past experiences. So let's work out we know the mass and the atomic mass of the metal. So the moles of the metal we can work out quite easily as 0.1 divided, so the 0.1 up here, divided by the 51. So the moles of the metal come out at 0.00196. And the moles of the hydrogen gas we can work out because it gives us the volume of gas made and the molar mass. The volume of hydrogen gas is 43.9, so that's 0.0439 decimeters cubed divided by 22.4, and that comes out at 0.00196. Now, how can I use that to help me work out the new oxidation state of the metal? Well, what we said here is that the ratio of the metal to the amount of hydrogen that's being made is a 1-to-1 ratio. Now, for me to make the hydrogen, okay, 1 mole of the hydrogen, there has to be 2 electrons gained by 2 hydrogen ions. Now, that tells me, therefore, that the ratio of the metal to hydrogen ions has to be 1-to-2. So therefore, what that's telling me is that this metal here must be losing 2 electrons. This metal here must have lost those 2 electrons. So the X value here must be 2, because the 2 electrons lost by the metal have to be the 2 electrons gained by the 2 hydrogen ions, because we worked out the ratio of metal to hydrogen ions is 1-to-2. So therefore, if this metal starts off in its 0 oxidation state, which it does, and it loses 2 electrons, the new oxidation state must be 2 positive. Okay, so that's how you do that part. The second part then, what we're doing is we're taking that, what is now 2 plus, and we are further oxidizing. It says complete oxidation here to another oxidation state. Now, we don't know what that is, But what we do know is that it's larger than 2 plus because it goes to complete oxidation from its lower oxidation state. So this X, okay, whatever it is bigger than 2 plus, or bigger than 2. Now how do we work out what it is? Well, we know the moles of permanganate ions because they are 58.8 cubic centimeters at 0.02 moles per decimeter cube. So 0.2 multiplied by 0.0588 tells me that I have 1.176 times 10 to the minus 3 moles of permanganate. Now, based on your prior knowledge, you should know that when permanganate ions undergo oxidation or reduction, or are used as oxidizing agents, they will require 5 electrons per mole of permanganate. So the number of electrons that are being transferred, if you like, in this reaction is equal to 5.88 times 10 to the minus 3. So that's the number of electrons that must be being lost by whatever moles of metal we have. And the moles of metal we had, we worked it out earlier, at 0.1 divided by 51 was 0.00196. So we can now work out a ratio of those moles of metal 2 plus ions to moles of electrons. Okay, so the moles of electrons 5.88 times 10 to the minus 3 divided by 1.96 times 10 to the minus 3 tells me that that is 3 to 1. So in other words, it's 3 electrons per 1 mole of the metal. So there's 3 electrons lost per 1 mole of the metal, 2 plus ions. So therefore the metal must go from plus 2 or 2 plus oxidation state up to the plus 5 oxidation state. So the answer to the last part, the high oxidation state of the metal, is that it is now 5 plus. So tricky little question if you weren't aware of it or familiar with the style of it, guys, so make sure you are. Okay, hopefully you understand that. The full worked answer from the PowerPoint, a little bit neater and tidier than mine, is on this page here, so maybe if you want to have a look at that as well. Okay, so I'm going to go to the next question now. Okay, so a totally different type of question, much wordier. Obviously you've got to sift through this and work out what's actually going on down here. So we take some 300 cubic centimeters of a particular solution, a solution that's made up of iron 2 chloride and iron 3 sulfate. And what we need to do here is we've got to work out basically in this solution how much iron 2 chloride and how much iron 3 sulfate was actually used to make the solution up in the beginning. And we've got two separate titrations. One will allow us to work out how much iron 2 chloride was in it, and the other will allow us to work out how much iron 3 sulfate was in it. So let's look at the first one. We took 300 cubic centimeters of the solution, and from that we titrated, or took out 25 cubic centimeters of the solution, titrated against potassium permanganate, and we got 12.5 as our mean titer. Now, this solution contains iron 2 and it contains iron 3. The really important part of this is that you realise we're going to titrate these against permanganate ions, is that the iron 3 in there does not react with permanganate. So these titers are only going to give us a measure of the amount of iron 2 that is present in the solution. Okay, now let's have a look at where we go from there then. So we started off with 300 cubic centimeters of the solution. We took out 25 cubic centimeters for the titration. So that's a 1/12 of the volume, and along with that will only come a 1/12 of the moles. So at the end we have to remember we're going to have to scale back up by a factor of 12. So have that in the back of your mind. We also know that iron 2 reacts with permanganate. Okay, now we don't need the whole equation, but you do need to know that they react in a 5-to-1 ratio of iron 2 to permanganate. That's crucial. If you don't know that, which you should know from previous learning, then you're not going to get this correct. We know that the permanganate in this first one was 0.02 molar concentration, and that the volume was 0.0125 decimeters cubed. So we can work out the moles of it from that. It's okay, and the moles of it come out at 2.5 times 10 to the minus 4. Okay, Now, I can work out the moles of iron 2 in the solution then, and that comes out at 1.25 times 10 to the minus 3. So that, remember, is in 25 cubic centimetres. So if I take that and I multiply it by 12, that will tell me how many moles of iron 2 I have in my 300 cubic centimetres, which comes out at a nice 0.015 moles, and that's in the of iron 2. We'll just keep labelling it to keep the examiner happy. And that's in now my 300 cubic centimetres. So I've got moles of iron 2 in 300. Okay, I can therefore just check how many moles of iron 2 chloride I would have. Well, 1 mole of iron 2 chloride contains 1 mole of iron 2 ions. So if I've got my moles of iron 2 ions, which I have, I've therefore got my moles of iron 2 chloride. So I've got my moles of iron 2 chloride. All I've got to do then is multiply it by the RFM of iron 2 chloride, which is the 56 plus the 71 is 127. Multiply that by 0.015, and that gives me an answer of 1.905 grams. So that original solution was made up using 1.905 grams of iron 2 chloride. Okay, let's go and see how we're going to work out the number of, or the mass of iron 3 sulfate in this. So following this, the technician treated 25 cc's of the original solution with acidified zinc to reduce the iron 3 to iron 2. So the original mixture, remember, contained iron 2 ions and it contained iron 3 ions. And in the first titration, all we did was titrate these iron 2 ions, but what we've now done is we've converted the iron 3 that was in there back to iron 2, and we're going to titrate those additional iron 2 ions with the permanganate. So if we look at it, this time it took 0.02 molar potassium permanganate, 17.8 cubic centimetres was needed. So there's an increase in the titration value from there to there. The concentration of the permanganate is exactly the same, and the reason for the increase is because we're now titrating the number of iron 2 ions that were in the original solution plus the iron 2 ions that have been made by the reduction of the iron 3 back to the iron 2. Okay, so we've got to use this to work out how much iron 3 sulfate was in. Well, there's a few different ways to do it. The way I would do it is 17.8 cubic centimetres minus the 12.5 cubic centimetres. Okay, so that gives me 5.3 cubic centimetres of additional permanganate solution. Okay, at 0.02. That is reacting with what was essentially originally iron 3. So I can work out the moles of iron 3 that were in there by calculating, let me see, my 5.3 to 0.053 times 0.02. Okay, so that tells me that the additional moles of permanganate is 1.06 times 10 to the minus 4. Now remember, I need to multiply that by 5 because the ratio of permanganate to iron 2 is 1 to 5, so I multiply that by 5. And that tells me that I have in my solution 5.3 times 10 to the minus 4. That is the additional number of iron 2 ions after the reduction, which is equal to the number of iron 3 ions in the original 25 cc's. So if I take that and I multiply it by 12, that tells me that in the 300 cubic centimetres I had 6.36 times 10 to the minus 3 moles of iron 3. Now here's where we need to be a little bit careful, because the formula of iron 3 sulfate is as so. So every 1 mole of iron 3 sulfate contains 2 moles of iron 3 ions. So this is the moles of iron 3 ions, remember. So I have to actually divide that by 2 to get the moles of iron 3 sulfate. So the moles of iron 3 sulfate are not the same as the moles of iron 3, unlike the moles of iron 2 chloride and iron 2. So that is 3.18 times 10 to the minus 3. I've got now my moles of iron 3 sulfate in my 300 cubic centimetres. I need to multiply that by the RFM of the iron 3 sulfate. That is 400. Okay, and that gives me an answer of 1.272 grams. So that's how much iron 3 sulfate was in the original mixture, and the previous one was how much iron 2 chloride was in the previous mixture. Hopefully those help, guys. They're tricky enough when they pop up, and they don't pop up very often, so you need to be prepared for them.